Every time a satellite streaks across your night sky, it looks like a bright star moving too fast to be real. We often assume this glare comes from shiny metal or bad luck with angles. But what if we could turn these orbiting giants into optical ghosts? The solution isn't paint. It is a material science breakthrough in nano-texturing that traps light like a deep space camera, turning the biggest hardware constraint of mega-constellations into an invisibility cloak for our view of the universe. The common misconception is that making satellites less visible is as simple as applying dark black paint to their hulls. We tend to think of black as just a color choice in a catalog. In reality, standard black coatings used on spacecraft today still reflect far too much sunlight to protect astronomical observations. When we look at the night sky and see these bright streaks, it is because conventional pigments scatter light rather than absorbing it. The breakthrough here moves us beyond chemical absorption into physical geometry. It relies not on a pigment that looks dark in visible light, but on growing microscopic carbon nanotubes that act as an optical trap. This transforms the satellite's exterior from a reflective object into a literal light sponge. To understand why this matters, we have to look at how standard black paint fails us. Even high-performance coatings like NASA's Z36 are designed for thermal control and durability in space, not for hiding satellites from telescopes on Earth. They still reflect enough sunlight that they create bright trails across long-exposure images taken by observatories. The new approach mimics natural structures found in nature, specifically the moth eye effect, used to reduce glare in deep space camera sensors. It is a shift from asking what color something should be to asking how its surface geometry interacts with photons at the nanoscale level. The physics of this light trapping relies on forcing incoming sunlight into an endless series of bounces inside microscopic structures. Researchers have developed surfaces using vertically aligned carbon nanotubes grown via catalyst-assisted chemical vapor deposition, or CVD. Unlike a spray gun that deposits a layer of pigment on top, this process grows the coating directly onto the satellite skin. Carbon-rich gases flow over substrates at approximately 750 degrees Celsius inside a heated tube. Under these conditions, carbon atoms self-assemble into vertical arrays that look like forests under an electron microscope. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. When sunlight hits this forest of nanotubes, it does not bounce back out immediately. Instead, the photons enter between the tiny tubes and are forced to reflect repeatedly from one wall to another with every pass. Each internal reflection absorbs a fraction of the energy until the light is fully trapped and converted into heat rather than being reflected back toward Earth. This mechanism allows these nano-textured surfaces to achieve up to 99% reduction in light reflection compared to conventional satellite finishes. That represents a tenfold improvement over standard black paint, effectively lowering the apparent brightness of satellites by a factor that brings them dangerously close to the limit recommended by the International Astronomical Union for non-interference with astronomical data. This is not just theoretical physics, it addresses an urgent crisis in ground-based astronomy. The Vera C. Rubin Observatory, which surveys vast swaths of the sky every night, has already documented how standard satellites produce bright trails that ruin scientific images. In summer nights when observation windows are longest and satellite density is highest, these streaks appear in roughly 1.2 out of every 1,000 images taken by conventional V1.5 architectures. By implementing these ultra-black surfaces on newer hardware designs, engineers can reduce this rate significantly without altering the satellite's orbital mechanics or software stacks. The manufacturing reality reinforces why this is a true engineering breakthrough rather than a cosmetic tweak. The coating must be grown in situ because it needs to survive the violent vibrations of launch and the harsh thermal cycling of space where temperatures swing wildly between sunlight and shadow. A simple layer of paint might crack, peel, or degrade under these conditions. But carbon nanotubes grown at 750 degrees Celsius form a mechanically robust structure that integrates with the substrate itself. This ensures the optical properties remain stable for years in orbit without requiring maintenance or software updates to function as an invisibility cloak. We also have to consider why we cannot just solve this by lowering satellites into lower orbits where they are less visible due to atmospheric drag and collision risks. While dropping altitude from 550 kilometers to 350 kilometers can reduce sightings by about 40%, it introduces significant safety hazards for the constellation itself. It creates a crowded debris field near Earth's surface. The nano-textured coating solves the brightness problem directly at the hardware level, allowing satellites to remain at their optimal operational altitudes while becoming optically invisible during critical observation windows. This proves that solving global problems like light pollution requires deep engineering of the physical layer rather than just software adjustments or orbital tweaks. This shift fundamentally changes how we engineer space infrastructure. It bridges the gap between high-level manufacturing processes and everyday stargazing, showing how a materials science breakthrough directly protects scientific infrastructure from being blinded by our own expansion into orbit. For curious viewers who have wondered why satellites are so bright despite looking dark to us in daylight, this answer reveals that it is not about color. It is about geometry. By growing carbon nanotubes, engineers create a surface that traps light like a deep space camera sensor rather than reflecting it, turning the biggest hardware constraint of mega-constellations into an optical invisibility cloak without changing how these machines fly or operate in space. The stakes are high because as we plan for thousands of new satellites to power global connectivity and internet services, the glare problem only grows worse with every added unit. If we rely solely on orbital adjustments or software mitigation strategies managed by other teams, we risk making parts of our night sky permanently unusable for astronomy. But this hardware solution offers a path forward where we can keep expanding mega-constellations without blinding our view of the universe. It demonstrates that the physical layer behind the technology, the specific way atoms are arranged on a surface, determines whether our technological progress comes at the cost of losing our connection to the cosmos above us. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.